Welcome back, everyone. We now have been scared from Melbourne, and here tell us about connecting W-algebras and the
Thank you for the introduction, and also thank you for coming and for this opportunity to talk. It's my first time in Spain, and it's a very nice. I hope to come back. Okay, so today I will discuss about some recent works which aim to connect W-algebras, and we will also take a look for the consequence of their implementation. And I will report on two works with Thomas Creutzig, Linshaw and Nakatsuka for the first one, and Chris, Raymond, and David Ridout for the second. Okay, I'm not sure a lot of people here are very familiar with vertex algebra. I don't want to give the definition. I think Joyce already gave the definition, so it's enough. Instead, I'd like to just draw a big picture and give some motivation to look at the subject. So vertex algebras are kind of complicated structure, algebraic structure, but they are quite interesting because they can allow us to relate many different areas. So in fact, we can associate to a vertex algebra many invariants. For instance, we can look at the group of automorphism, which in some nice case will be an algebraic group or a finite group. We can also associate a character, which defines sometimes modular forms, and so on and so forth. So we have plenty of invariants occurring in a lot of different areas. If I need to maybe emphasize one connection between all this area, it should be the historical application of vertex algebra. So indeed, vertex algebra were used to prove, for instance, the Munchausen conjecture, which relates the representation of the monster group and some modular J function. And vertex algebra were recently appeared in also plenty of important problems, very recent problem like the HET conjecture with moduli space or the Langlands law. Okay. Oh, sorry. Let me come back. I forget a very important thing. So vertex algebra, in fact, were known by physicists a long time ago. They are kind of mathematical counterpart of quantum field theories. So we have a deep connection with mathematical physics too. So even if they were known by physicists, as I said, for a long time, in fact, the mathematical formalism was introduced by Borchardt in the middle of the 80s. And its definition allows us to look at vertex algebra like a vast generalization of infinite dimensional Lie algebra or associative algebra with a derivation. Okay, so we have a unit which we usually call vacuum, and we also have infinitely many products that are encoded in some formal Lorentz series. And in our case, for this talk today, we will look at V08, vertex operator algebra. And so for this, we have an additional structure given by what we call the conformal vector, which defines the grading on our vertex algebra. If you look at vertex algebra in the literature, the first example you will encounter will probably be the following and come directly from infinite dimensional Lie algebra. So as a representation of such Lie algebras. So that's the case, for instance, of the Heisenberg vertex algebra, or also more generally for affine vertex algebra, which come from affine Kac-Moody algebra. So these two first examples are kind of the same family, and another very close construction is the one of Virasoro vertex algebra, which follows from the Virasoro Lie algebra. Okay, so these families come from the algebras. As a representation of the algebras, we could use tools of the algebras to try to study them. But sometimes it will be convenient to look at a more complicated object and then come back to the first object of interest. And this more elaborated object that I will use will be W-algebras. So W-algebras will be another family of vertex algebras, but because they are not Lie algebras, we cannot, I mean, we really need to use the formalism of vertex algebra to look at them. Okay, so as I promised, no definition. So instead, I will take a look to an example, first example that I will construct with you. So please consider an easy Lie algebra. I like to consider SL2, and I will look at a complex simple Lie algebra here. So I recall the definition, but I guess that most of you are familiar with it. So we consider this 2 by 2, the set of 2 by 2 matrices with 0 trace. And we take the commutator to be, the Lie bracket, sorry, to be the commutator of matrices. So this defines SL2. And from this finite dimensional Lie algebra, I can construct a certain affinization, an infinite dimensional Lie algebra called the affine Kac-Moody algebra, which is in fact an extension over the loop algebra, the algebra of polynomials. Okay. So in this Kac-Moody algebra, I have a central element that I denoted by K here, which commutes with everything. And other generators are given by the monomials with Lie brackets brackets. And bit technical, but I fix a triangular decomposition of this Lie algebra, which is quite usual, in fact, and which depends on the power of the monomials. Okay, so if I look at representation theory, so in fact, representation theory of SL2 are well known in general, and there is an easy way to construct a representation of the affine Kac-Moody, starting with an SL2 module. So in my example here, I will look at an irreducible highest weight representation. So it basically means that the highest weight vector that I denote by this cap lambda here will be vanished by the action of E. And so my module is generated by the power of F acting on the highest weight vector. So this, now if I take an induction of this module, a kind of affinization, where the positive part of my triangular decomposition acts trivially, I can define a Verma module over the affine SL2. Okay, so this is done for any highest weight representation. Even if I start with an irreducible SL2 representation, I don't necessarily get an irreducible SL2 hat representation. And so I define the simple quotient, the unique simple quotient. And now if I take lambda to be 0, meaning that if I start with the trivial representation of SL2, the Verma module that I construct can be endowed with the structure of VO, provided that the level K here is non-critical, so different from -2. Okay, just for the picture, so this picture here represents the module or the VOA, depending on which side you prefer. So in fact, you can view VK of SL2 like a collection of states, where we will have the action given by the modes, or you can view VK of SL2 like a collection of states. Both pictures are exactly the same. It's just a dictionary between the two languages. Okay, so we have our first VOA, and if we want to look at the representation of this VOA, in fact, the affine vertex algebra here will capture the module of affine SL2, which are called smooth. So which means that our modes here act by 0 when I take n to be larger. And if I want now to restrict to positively graded representation, and in particular irreducible positively graded representation, then there are in one-to-one correspondence with the algebra of 0 mode of our vertex algebra. So in our case, an associative algebra generated by E0, H0, and F0, so just the enveloping algebra of SL2. Okay, and the correspondence is very explicit, given by the constructions that I mentioned just before. So at first sight, here the zoo algebra doesn't depend on the level. So it means that the representation for the affine vertex algebra doesn't depend on the level either. And if we want to see a certain dependence, then we have to look at the simple quotient. And in fact, the simple quotient is interesting when we look at K to be admissible. So that are the fractional levels actually in the world. For other levels, in fact, the vertex algebra is already simple, so we don't have to do it. Okay, so in the following, I want to consider such an admissible level, and I will distinguish two cases. First, let's assume K to be an integer, non-negative integer, so denominator is just equal to 1. Well, in that case, we know how to describe the simple quotient of the affine vertex algebra, and we also know how to construct this image in the zoo algebra. So here we have a certain singular vector, a quotient generated by e to the k plus 1, to the power k plus 1. And in fact, representation theory of this algebra here is very well known. It's just the SL2 representation, which are finite dimensional with dimension smaller than k plus 1, smaller or equal to k plus 1. And if I compute the affinization, the induction in the affine SL2, then I get what we call the integrable representation. All these representations have a graded component which are finite dimensional, just like on the picture here. So on this picture, you should imagine that each line, horizontal line, is a graded space for the control mole vector. Okay, so you have finite dimensional graded space, which means that we have only ordinary modules. And in fact, this case where we have only ordinary modules and a finite number of irreducible modules is specific to the rational case. So here, the simple vertex algebra is rational, which means that our category is finite and semi-simple. And Wang, in addition, showed that in that case, we also have very nice structure of modular tensor category. So we can in particular look at the fusion rules applying the Berlin formula and compute explicitly these fusion rules, which match the fusion rules of in the quantum groups. Okay, so second case, now that the first case is completely done, is when we are looking at admissible levels which are not integers. And in fact, in that case, we have some modules which are not ordinary modules, so with infinite dimensional graded space. For instance, we have what we call relaxed module. So in fact, relaxed module is, we don't assume the top space to be a finite dimensional module necessarily. So we don't assume that we have a highest weight vector or lowest weight vector for the algebra of zeros. So in particular, we can have some module like the d plus and d minus, which are infinite in one direction, or the module with ER S lambda, which are infinite in both directions. The laters here will be called fully relaxed, and the middle ones will be semi-relaxed in the form. So if we want to do like in the first case, so if we want to look only at ordinary modules, in fact, we can check that they are still modular, so their characters are still modular. However, if we try to apply very naively the Berlin formula to compute the coefficient of the fusion modes, so the Berlin formula is right in here, we will have some coefficients which are negative integers. So we have negative multiplicity here. And this suggests that maybe we are missing some module. We are not looking at the good category of module. And in fact, a good candidate for this nice larger category would be the category of relaxed module together with their spectrum. And that's what David Ridout and Thomas Creutzig did. So in fact, they looked at character of fully relaxed module and relaxed module in general, and they checked their modularity. And for the fully relaxed module in particular, they noticed that we can factorize the character to make appear here the character of what we call the Virasoro minimal model. I will explain in the next slide. But these Virasoro minimal models are in particular known to be modular. Okay, so since I talked about Virasoro minimal model, I need to recall what is the Virasoro vertex algebra. So the construction is very similar to what we've done for VKSL2. So I won't give too much detail, but in fact, we start with the Virasoro algebra, which is central extension of the weak algebra, and then we take a representation induced again. So if you're not very familiar with representation, in fact, you might like to think about the Virasoro vertex algebra just by vertex algebra generated by one field, which satisfies the commuting relation on the top. And this Virasoro vertex algebra is a very important example of vertex algebra because, in fact, a copy of such algebra exists in any VO. And in our construction, we have this little parameter C here, which plays the role of the capital K in our first example, and which is called the central charge. And in fact, for some values of this parameter C, we know that our vertex algebra, the Virasoro vertex algebra, is rational. So semi-simple with a finite number of irreducible and so on. Okay, and these irreducible are exactly the ones that we call Virasoro minimal. And so this category this object here from modular tensor category. So it means that in fact we kind of make a relation between the affine vertex algebra and this Virasoro algebra. So at first sight, we don't have any idea why this Virasoro algebra appear. But if we want a clue, we have to look, in fact, in the physics literature. In the 80s, Semikatov defined a certain embedding between the affine into the Virasoro vertex algebra time a certain other vertex algebra called half lattice. We don't need to know what it is for the purpose of this talk. But this embedding is in particular very interesting because it's a conformal embedding, which means that it preserves the conformal structure, maps the conformal vector to the conformal vector. And if we want to look at the quotients, in fact, this embedding is also preserved when we take simple quotient. If we assume the level to be admissible but non-integer. So exactly the case we were interested in. And for such level, when our central charge here is a central charge of rational Virasoro vertex algebras. So what we do is, using this embedding, is find a natural way to construct fully relaxed module, just by taking a module of the Virasoro vertex algebra and a module of the half lattice. And so this module will allow us to look at the modularity of the fully relaxed module using the modularity of both families here. Okay, so apparently we have now an explanation for affine SL2. We know how to look. I mean, we have a good candidate for the nice category of module to look at, the relaxed module, but we would like to extend to SLN. And if we want to extend to SLN, then we need to find something which will play the role of the Virasoro to have such an embedding. And because I'm interested in W algebra, you might think that it will be a W algebra, and you would be right. So let's consider. Let me just explain how to construct this object. So here we consider set of nilpotent element, so the nilpotent pole in SLN. This is a finite union of disjoint orbit under the action of the group, the group. And in fact, if you don't know anything about nilpotent orbit and so on, you can just view it as a set of partition, because this nilpotent orbit for SLN are parameterized by the partition of N. And we have a partial order on this set of partition, given by the following. And this also corresponds to the partial order given on the nilpotent orbits by taking the closure and the Zariski topology. Okay, so now that I described a bit my nilpotent pole, in fact, I can take for each partition, I can define a W-algebra by applying a certain quantum Hamiltonian reduction to the affine vertex algebra. So it's a complicated process, but we don't really need to have too much detail on it. If you are familiar with finite W-algebras, then you can view it as an affinization of of this object, and they will also quantize the distance. So all these objects are related in some sense. And to relate with the examples that we had before, in fact, if you take the nilpotent orbit with the trivial one, your procedure don't do anything, so you recover the affine vertex algebra. And if you take any, if you take the non-zero nilpotent orbit of SL2, then you recover the bilateral vertex algebra. So it seems like it will generalize nicely what we had before. At least it matches the previous condition of SL2. And in fact, if we look at more examples, we can construct more inverse Hamiltonian reduction also for SL3. So SL3 inverse Hamiltonian reduction, so the embedding that we had before for SL2 can be generalized to SL3. They have been brute force again. So for the first, we have from the minimal nilpotent orbit embedding into the principal one, which has been proved by Adamovich, Kawasetsu, and Ridout. And Paley and Ridout, in that case, checked that for k to be greater than 3, so when the big one is rational, we have a modularity of Ridout's module again. And it was quite similar to SL2 in the sense that the embedding is quite similar to what we had for SL2, with just a null lattice. And in fact, for SL3, from the minimal to the affine, or more correct to say, embedding the affine into the minimal, we have in addition a certain beta gamma system, which is a certain vertex algebra, which is also well known. So this embedding has been defined by Adamovich, Creutzig, and Genera recently. And with my collaborator Raymond and David Ridout, we checked the modularity when Q is equal to 2. So the denominator Q to be equal to 2, meaning that the W algebra on the right is rational. So in particular, we checked the Berlin formula and find that all the multiplicity that we get are a positive integral. Okay, so usually when something works for SL2, we check for SL3, and when it works also for SL3, we want to say that it will work in general. So here we want to say that relaxed module will be in general the good category of module to consider to have a kind of modular tensor category. Okay, so for this, we will try to apply the same procedure. We want to find embeddings between our affine and a certain W algebra, which will be rational. So first step will be to construct all these possible embeddings. And for this, the brute force approach is not the well approach to consider, because I mean it's not realistic, because we don't have a general description of the W algebras. However, we have a very important result of Paley using screening operator, so certain kernel of linear maps,
Sorry, what is the meaning of the colors? What distinguishes the yellow?
It's my next comment. So in fact, our purpose was to relate the affine one to a certain rational W-algebra. And we have a classification of such rational W-algebra by Arakawa and Vanek. So for admissible level, if you fix a denominator 2, so for instance, they take 3, 2 to be equal to 3, then the orange one, the yellow one, sorry, 3, 3 will be rational. So these yellow ones are the possible rational W-algebras. And so you will start with your partitions 3, 3, and you will go back to the affine. And doing that, you will reconstruct the relaxed module and pull back also possibly, I mean, theoretically, you pull back the modularities. So I say theoretically because in practice, in fact, you can encounter some, I mean, we haven't fixed all the problem. So for instance, you might have some module with infinite dimensional weight space. So you need to find a new way to define TRHW. Okay, so I think it's almost finished. So let me just do the conclusion. So in brief, this inverse Hamiltonian reduction on beddings will just allow us to create bridge between a certain rational W-algebras and the affine vertex algebra. And using this bridge, we can reconstruct the representation theory of affine vertex algebra. In fact, we expect a bit more connection on than what I draw on my picture here. And in particular, we expect to connect all the W-algebras with the partial order given by the nilpotent orbit closure. So this is a lot of work in progress for many teams, and in particular with my collaborator Peli, Fussman, and Nakatsuka, we construct all the arrows for SF. Okay, I will stop here. Thank you for your attention.
Thank you very much. Questions?
The white partitions, is it they're just not known if they'll never be rational, or is the understanding that they are never rational?
It's not known. In fact, yeah, we know some level where it's rational, but we don't know if, yeah, we don't have the full classification of rational and
But with the Arakawa and Honecker and yellow ones, there's always a way to terminate in one of their.
Yes.
Okay.
Yes. In fact, for each admissible, we will have at least one of this yellow, which is rational.
Okay.
Yes.
We need generic level,
Yeah.
generic case. Mentioned this correspondence between related representations and representations that we have on the right?
Yes.
But what category we get is category O or
Positively graded modules. So
on the others, on family others.
so it's, oh, it's all irreducible on the affine side. Sorry, on the
But not final dimension.
no, not finite dimension.
Category O, but is it category O?
Not necessarily. Not necessarily for the zoo algebra. So for the in the SLN side, you can take any irreducible.
It doesn't need to be classified.
No, it doesn't need to be actually.
On the second side, not category. Not category.
Yeah, it's not category.
It's just weight options. Okay. You're not saying anything about different categories, right? You're just saying it's one of the simple.
Yes.
But you're not, but there's a statement about different categories. Something. Some boundary.
I don't know.
There is a statement. Say, what about accessory? Is there a factorial?
One more question. If not, then that's fantastic, I guess.